Again, seriously, this is the third snow day in a row. Unbelievable. This is Groundhog Day, and we're going to be talking about reference table G and F today. But look at this. I'm getting sick of it. This is like Groundhog Day. 3 snow days in a row, almost 2 feet of snow. So, what we're doing today is New York State reference table F, solubility for aqueous solutions. Very interesting table. This is table F, and this is combined with double replacement reactions. And these can be the reactants, and these could also be some of the products. So we'll go over double replacement after we talk about this chart. So, on the left side, ions that form soluble compounds. In other words, these hooked up to anything, when you put them in water, will form soluble compounds and it will form a solution. So, any group 1 ion, I don't care if it's lithium, sodium, potassium, rubidium, cesium, francium, anything hooked to those ions will be soluble when you put it in water. Ammonium, anything hooked to ammonium will be soluble. Nitrate also, acetate also, hydrogen carbonate, chlorate. Now, these are very interesting down here. Any of the group 17 elements, any of the halides, fluorine, chlorine, bromine, iodine, will be always soluble except if they're hooked to silver, lead, or mercury. If they're hooked to silver, lead, or mercury, they are going to be insoluble and they will precipitate out of the solution. Sulfates will always be soluble except if they're hooked to silver, calcium, strontium, barium, or lead. If they're hooked to any of those ions, they will also precipitate out of a solution. Now, on the other side, these are ions that form insoluble compounds. So anything hooked to carbonate will be insoluble, except if it's a group 1 metal or if it's hooked to ammonium. So if it's a group 1 metal or hooked to ammonium, the carbonate will be soluble in water. Chromate, always insoluble unless it's hooked to a group 1 metal, calcium, magnesium, or ammonium. Phosphate, always insoluble when it's hooked to something unless, like we said before, if it's hooked to a group 1 ion or ammonium. Sulfides, same thing, always insoluble unless it's hooked to a group 1 ion or ammonium. Now this next one is pretty interesting. These are hydroxides. And hydroxides will be insoluble unless it's hooked to group 1 and ammonium, like the other ones, or calcium, barium, or strontium. So they will be soluble if they're hooked to hydroxides. All right, that's the chart. That's how we use it. And now we're going to go into double replacement reactions and how to figure out if the products are soluble or insoluble using reference table F. So this is our first double replacement reaction. We have aluminum sulfate plus calcium bromide. So usually, hopefully, all the time, the reactants are always soluble. But let's check it out. So we have aluminum sulfate. So here's the sulfates right here, and they will always be soluble unless they're silver, calcium, strontium, barium, or lead. So aluminum sulfate is totally soluble. Now let's look at calcium bromide. There's bromine, always soluble unless it's hooked up with silver, lead, or mercury. So calcium bromide, always soluble. So both reactants are totally soluble. Now, to get the products, it's really easy. You just flip-flop the first two positive ions. So in other words, aluminum will flip-flop with calcium. So your two products will be aluminum bromide plus calcium sulfate. So, aluminum bromide, calcium sulfate. Let's see if there's any reaction at all. If there's no reaction, both products will be soluble. If there is a reaction, that means one of these products will be insoluble and precipitate out of the solution. Because remember, this is aluminum sulfate's a solution, and that calcium bromide is a solution. You pour them both together, and you get aluminum bromide and calcium sulfate. If something falls out when you pour them together or precipitates out, there is a reaction. So let's check them out. Aluminum bromide, calcium sulfate. So here's bromide. Aluminum bromide is soluble. Calcium sulfate. Here's sulfate. Oh, there's calcium right there. So when calcium is combined with sulfate, it's insoluble. So what we're going to do is this. We know that this right here, calcium sulfate, is insoluble. So I put an arrow going down, which means it precipitates out. So now we do have a reaction, and it will only go one way because we are losing one of the products. This reaction will never be at equilibrium because it can't go backwards because one of the products is falling out. All right. So now what we have to do down here is write the true formulas. Okay? All right, so here we go. Aluminum sulfate. We have Al plus 3, and sulfate is SO4 minus 2. So we crisscross. 2, 3, plus we have calcium bromide. Ca plus 2, Br minus 1, crisscross. Remember, this reaction can only go one way because we are losing one of the products. So now we have aluminum bromide, but the good thing is this. We have all our oxidation states up, so we don't have to find any oxidation states on the other side. Okay? So now we have aluminum bromide, Al plus 3. And bromine is Br minus 1. And we got a crisscross 3. Now, a common mistake that everybody makes is, you see that 2 right there next to the Al? That was a crisscross product. Never ever bring the crisscross products over to the other side. All right, so that 2 you never bring over there. And here we have Br3. You can't bring that over to the other side because that's a crisscross product. All right, you have to make whole new compounds over here. The only time you bring a number over is if it's in a polyatomic ion. If it's part of the polyatomic ion, you bring it over. If it's not, don't bring it over. So we have plus, and I'm going to put this, since it's falling out, plus calcium sulfate, Ca plus 2, SO4 minus 2. So look it, we have a plus 2 and a minus 2, that equals 0. You don't have to crisscross. And remember, that 4 comes from right there. You have to bring over, if it's part of if it's a part of a polyatomic ion, you got to bring it over. But if it's a crisscross product like that 2 right there, or that 3, or that 2, do not bring it over to the products. So now we have this. Now we know that calcium sulfate falls out. Put an arrow down. It's a precipitate. The reaction goes one way like we said before. Now we have to balance the equation. And I like to balance it by polyatomic ions. That's probably the easiest way. So let's do this. And we have 3 sulfates right there. We only have 1 sulfate right there. So we're going to put a 3 right there. But that makes 3 calciums. We come over here, we only have 1 calcium, so we're going to put a 3 there. But now that makes 6 bromines. 6 bromines, we have 3 there. So if we put a 2 in front of the aluminum, the 2 blows through everything. So it'll be 2 times 3. We have 6 bromines and we have 2 aluminums. But watch, our 2 aluminums, we come back over here and oh look, we have 2 aluminums right there. So this equation is balanced. Now, that's how you do a double replacement. But there's more to it. Now we have to break this down. We have to break this down into ions. So now we have 2 aluminums. So we go like this. 2Al plus 3. Plus we have 3 sulfates. 3SO4 minus 2. And we have 3 calciums. 3Ca plus 2. We have 6 bromines plus 6 Br minus 1 yields. We have 2 aluminums, 2Al plus 3, and we have 6 bromines, 6 Br minus 1. And then we have this, but we can't break it up because it's falling out. So we're just going to go like this, plus 3 Ca plus 2, SO4 minus 2, arrow down. So now we have everything broken up. Okay? Everything's broken up. The only thing we can't break up is what's insoluble, and that's calcium sulfate. The next thing we have to do is get rid of the ions that are the same on both sides. These ions actually brought what's going to react into the reaction. They are called spectator ions. It's like if I had a son and he played basketball, I would drive him to the game, he would participate, and I would sit in the stands and spectate. Well, what was my role? My role was to bring him, who's going to react in the game, to the game. So that's the same thing with spectator ions. They bring whatever reacts into the reaction. So let's see what we have on both sides. We have 2Al plus 3, 2Al plus 3. So we wipe those out. Those are spectator ions. Anything else? 3SO4, nope, that's included in the precipitate. 3Ca plus 2 in the precipitate. 6 Brs, oh, there's 6 Brs right there. So now we know that aluminum and bromine were spectator ions, and they brought sulfate and calcium into the reaction to react. So my bromine and my aluminum are called spectator ions. So the last thing we have is we have what really reacted. Okay. So what I'm going to do is I'm going to put what's left in the reaction, what actually reacted, above it, because I ran out of room down below. So I have 3SO4 minus 2 plus 3Ca plus 2 yields 3Ca plus 2 SO4 minus 2, arrow down. And that is the true reaction, all right, minus the spectator ions. So this is what SO4, when it combined with calcium, it formed calcium sulfate, which is insoluble and precipitated out, which means the reaction, there was a reaction and it fired to the products. It never reverses and it will go to completion. That is how you do a double replacement reaction. We will do one more. Here is the second double replacement we're going to do. So what do we have? We have ammonium phosphate and barium nitrate. So like I said, the reactants are almost always soluble, but let's take a peek on reference table F and make sure. So we have ammonium phosphate and barium nitrate. All right, so there's ammonium right there. Anything hooked to ammonium is going to be soluble. So ammonium phosphate, totally soluble. Barium nitrate. Well, nitrate's right underneath there, and anything hooked to nitrate is going to be soluble. So now we know that barium nitrate and ammonium phosphate are totally soluble. So let's see if there's a precipitate formed or not. So, we remember you take the positive ion, and flip-flop them. So we have ammonium nitrate plus barium phosphate. So ammonium nitrate and barium phosphate. Well, we know ammonium nitrate, well, there's ammonium, it's always soluble. To nitrate, it's always soluble. So ammonium nitrate is totally soluble. Okay? So now we have barium phosphate. So we come over here to phosphate. Phosphate's always insoluble unless it's combined with group 1 or ammonium. So, since it's combined with barium, and barium is not a group 1 metal, it's insoluble, which means it's going to fall out, which means it's a precipitate, which means the reaction will go to completion. It doesn't have a chance to be at equilibrium because they're losing some of the product. Okay, so let's check it out. So what we're going to do is we are going to write down the equation now. So ammonium NH4 plus phosphate PO4 minus 3. So that's plus 1 and a minus 3, so we have to go like this. We're going to put a 3 right there. You got to crisscross. You don't need to crisscross the plus 1 because it's given. Plus barium nitrate. Ba plus 2 NO3 minus 1, and we have to crisscross, and that's a 2 right there, yields ammonium nitrate NH4 plus 1 NO3 minus 1. And since that's a plus 1 and a minus 1, that equals 0. We don't have to do any crisscrosses at all. Plus barium phosphate. And we found out that barium phosphate is insoluble. So we're going to go like this. Ba plus 2 PO4 minus 3. We got to crisscross that 3 and that 2. And then we're going to go like this, arrow down because it's insoluble. Now, there is our equation. Like I said, it can only go one way because there's a precipitant. The reaction can't go backwards. Now we have to balance. And like I said, balance by polyatomic ions first. Now, remember, we didn't bring over that 3 because that was a crisscross product. We didn't bring over that 2 because that's a crisscross product. We only bring over what's in the polyatomic ion. So we had to bring over that 4 because that's part of the polyatomic ion. We had to bring over that 3 because that's part of the polyatomic ion also. All right? All right, so let's balance this thing. Pick something there's a lot of. Barium. There's 3 bariums there. There's only 1 there, so we're going to put a 3 right here. Now, after we put that 3, remember the 3, the coefficient blows through everything. So 3 times 2, I have 6 nitrates on this side. I only have 1 there, so I'm going to have to put a 6 right there. Now, that 6 means I have 6 nitrates, but that means I have 6 ammoniums. So I have to go over to ammonium. I got 3 of them. So if I put a 2 right there, that means 2 times 3, I got 6 of them. Now remember that 2 blows through everything, so that 2 means I have 2 phosphates. So I come over here, oh look, I already have 2 phosphates. It's balanced, all right? So this whole thing is balanced. Now we have to break it apart into ions. I have 6 ammoniums, 6 NH4 plus 2 PO4 minus 3 plus 3 Ba plus 2 plus 6 NO3 minus 1s yields 6 NH4s, 6 NH4 plus 1 plus 6 NO3 minus 1 plus the precipitate. Remember, you can't break that up. So we're going to go like this, plus Ba3 PO4 2, that's a plus 2, that's a minus 3, and that means it's going to be insoluble. We can't break that up. Now, we have to find out what the spectator ions are. And remember, the spectator ions are what brought in what's reacting. So, what brought in the Ba and the PO4? Well, there's the PO4, so the ammonium brought it in, and I have to have exactly the same numbers on both sides. If you don't have the same numbers, you messed up. So I've got 6 NH4s, I've got 6 NH4s. I have 6 NO3s, I have 6 NO3s. Remember, if those coefficients aren't the same, you got to go all the way back and make sure you balance the compound correctly. So the final reaction is 2 PO4 minus 3, 2 PO4 minus 3, plus 3 Ba plus 2, 3 Ba plus 2, yields that. Ba plus 2, PO4 minus 3, so we crisscross, 3, 2, and don't forget, arrow down. So this is your final reaction right there. This is what reacted. 2 PO4s, I got 2 PO4s, I got 3 Bas, I got 3 Bas. So this is your final reaction. And don't forget, you have to have the same coefficients in order to cross out the spectator ions. And that's where a lot of students make mistakes. If they don't have the same coefficients, you can't cross it out. Like I said before, you got to go back, and you must have not balanced the equation or an individual compound correctly. So you got to go all the way through and figure it out. So we've gone through 2 double replacements that have precipitated out. Well, what if the 2 products are totally soluble? Well, that means there's no reaction. When you pour the 2 liquids together, nothing happens. There's no reaction if the 2 products are soluble. Okay? So that is how you use reference table F. And that's how you do double replacement reactions. Okay, thank you.